I'm gonna pick one. I'm gonna delete this one and we reset the timer. So this is an easy question, so I'm gonna aim to finish within 10 minutes. Okay, so maximum depth of binary tree. Given the root of a binary tree, return its maximum depth. And the binary tree's maximum depth is the number of nodes along the longest path from the root node down to the furthest leaf node. Okay, so I'm starting from root node, and then I am gonna have 3 leaf. So this 3, 9. So if I see this example, output is supposed to be 3. So depth's gonna be the number of nodes. So if I go 3, 9, that's gonna be 2. And if I go 3, 20, 15, the number of nodes is gonna be 3. So even if I go to 3, 27, it's still the same 3. So the max number is gonna be 3. So I'm supposed to return 3. That's clear enough. And then the number of nodes would be, I might gonna have just empty tree. That's gonna be the edge case, and I'm supposed to have up to 10 to the power 4, and then I'm gonna have negative number at the body of the node. But I think it's not gonna be matter because we don't care about the value of the node. So I think what I'm going to do is I'm gonna do DFS, depth first search, and so that's gonna I'm gonna create the recursive function, and the recursive function gonna carry the number of node I've seen so far, and then when I reach at the leaf, I'm gonna just update the answer global variable with the maximum function if current number of node is more than the number of node I've seen so far. I'm gonna just update it to bigger number. So it's supposed to the answer global number should be 0, and then when I just update it, when I hear like 2 is gonna be updated to, when I reach here 2 is going to be updated by 3, and then eventually after finishing DFS, I'm going to just return the global answer variable. So that's what I'm going to do, and then time going to be O of n, where n going to be the number of node, and the space going to be the height of the tree because I'm doing the recursive function. So it sounds okay to do that if I see constraints. So this solution should be feasible. So I'm going to have 7 minutes to go. So I'm going to have answer variable, and then eventually I'm going to return this answer, and then I'm going to do recursion, and I have node and also column. Okay, and then if the leaf not node left and not node right, I'm going to update answer by the current number. And to do that, I need to non-local this answer variable. And then eventually what I'm going to do is recursion to this root node. And because this could be 0, so first I need to check if node, and if node is I'm have something I'm gonna do, but otherwise just do nothing. So actually I don't have to write anything. So if the root is empty, recursion not going to work, and then answer just stay with the 0 and then return 0. But that's supposed to be 0 if the tree is nothing. The depth should be 0. So I'm starting with 1. Okay, and then recursion to node left, and I'm gonna increment by 1, and also I'm gonna recursion to node right, and that's gonna be incremented. I still have 5 minutes. So I think I'm gonna just take time to validate this code is working. So um, 3 3 is obviously node exist, and it's not the leaf. So I'm going to the left, and when I add 9, I'm gonna have 9 2, and 9 obviously is a node, but I don't have any child, so also going to be updated with 2. And then coming back here, 3, and then I'm going to right, and here I'm gonna have nodes are going to be 20, and current number going to be 2, and it's not the child, so I go to the left, and at that time when I reach 15, the current number argument going to be 3, and then we have 15, but it doesn't have both children, so it's going to be the leaf. So answer would be updated with 3. And I think I'm going to skip 7. So I think this should work. So I'm going to run with the test case. Test case looks good. And I'm going to submit for all the test cases. And it worked. So basically this approach, time complexity is the O of number of leaf. And then space going to be the depth of the leaf for the recursion, because we call stack. That's it.